I'm going to get the recording going. So for this one, it says use the graph of f prime to tell where f is increasing, decreasing, and identify any relative extrema. All right. So this is kind of a weird question in the sense that they don't give us the original function like they did in numbers 1 and 2. They're actually giving us the derivative graph. So we need to draw conclusions about the original function based off of this derivative graph. But the good news is we don't actually have to find a derivative here, right? So what I can do is I can make a sign chart based off of what I see here and just kind of get right down to business, all right? So all right, so x, f prime of x in the conclusion, and then we build our chart from there, all right? But the thing is, how we interpret this graph is going to be a little bit different from how we might interpret an ordinary function f of x, all right? So if we go back to the previous problem, either of the previous problems really, we know that if the derivative is negative, that means the original function is decreasing. If the derivative is positive, that means the original function is increasing. So if we look at this graph here, I want to go focus in on this. We have, it's x against y, but the y-axis is really just talking about where f of x is, right? I'm sorry, f prime of x is. All right, so this whole graph is f prime of x. There's a little string mark here. Let me get rid of that. So anything that's above the x-axis here, that's a little too thick. Anything that's above the x-axis is going to be where f prime is positive. Anywhere below the x-axis is going to be where f prime is negative. All right. Just like if you were to graph a function, let's just say it's an ordinary function, y equals x squared. I'll say x squared minus 2. You have some parts of this graph that are above the x-axis and some parts of it that are below the x-axis. Anything over here would be where the y value is positive. Anything over here would be where the y value is negative. All right. So you can see here, I'm doing it kind of quickly, but you can see for any value that I select in this interval here from from whatever this x value is, it would be a negative radical 2, all the way over to the positive radical 2. All the y values that correspond with that would be negative. And anything beyond those points, all the y values are positive, all right? So it's no different when you're dealing with a derivative function. So what we have here, and I could actually even just kind of estimate this function. This is a derivative graph that, I can make up an original function that has this as its derivative, or I can just graph y equals something like ax cubed. This is definitely cubic, plus bx squared plus cx plus d, and then just play around with these coefficients until I get something that looks like this. I mean, we'd be looking at a negative a value. I probably want to shift it down. You're looking at something like this. I can kind of slide things around a little bit. I might be looking at something along these lines, ballpark. All right. Now, if I tell you that this is a derivative graph, then all of these y values, you see all these y values here, they're all positive. All of these y values, in this interval, it's kind of hard, I'll zoom in. All of these y values are negative, back to positive, and back to negative for the y values. And that little stray mark there is kind of aggravating, but that's the idea. And now if I tell you that this function that I plotted on Desmos is a derivative function, then I'm saying that the derivative is negative below the x-axis, the derivative is positive above the x-axis. Now add to that the cases where we're actually on the x-axis. Those would be instances where f prime of x is equal to 0. All right. So we can start drawing some conclusions here, because anywhere, and just going back to what we were talking about last class, anywhere where the derivative is positive has the original function increasing. Anywhere where the derivative is negative has the original function decreasing. And anywhere where the derivative is equal to 0, that could be a turning point, but it's definitely a critical value. I don't even know what I'm listening to. Anywhere where the derivative is equal to 0 is showing a critical value, and that's a possible relative extremum. So what I get here is a graph that, you know, it seems to be boundless. I can't really tell where this thing terminates, but it seems to be kind of flapping in the breeze here. So I'm going to assume that it goes on forever. If it goes on forever, then it's telling us that our first interval would be from negative infinity to the x value indicated by that first blue point, which appears to be -1. Then our next interval would go from -1 to +1, but we would stop at -1 to draw a conclusion for that. -1 to +1. I'm sorry, -1 to 0. That would be my second blue point. Then 0 to +1 would be my third blue point. We'd stop at 1 to draw a conclusion there. And then lastly, we got to assume that this is going to go on to positive infinity. We have no reason to think it's just going to stop. There's no solid endpoint there. So I would say going from 1 to infinity, right? At -1, 0, and 1, the derivative value is equal to 0. It's on the x-axis. On the interval of -infinity to -1, it's the green part. It's above the x-axis, so that would be a positive number. Between -1 and 0, it's below the x-axis, so that's a negative number. Clean that up. Between 0 and 1, it's back above the x-axis, so that's a positive number in terms of the derivative value. And then the last interval has it going below the x-axis again, so that would be a negative number. So it's the original function would be increasing, then decreasing. Just going to abbreviate. Increasing, decreasing. when there's a transition from increasing to decreasing, that shows a relative maximum. A transition from decreasing back to increasing, assuming it's a smooth function, continuous function, that would be a relative minimum. And then any transition that goes for a smooth continuous function from increasing back to decreasing, so high then low, going up then coming down, that would be a relative maximum. All right. So the conclusion, just to be clear about this, the conclusion that we're drawing has to do with f of x. Okay. So we're drawing a conclusion about the nature of the original function, or the function that led to this as a derivative. Right. So, without knowing what the function is, we can get a sense of what it would look like. And that would actually help us kind of estimate what that graph ought to look like, because if you know that you have a graph and it's kind of like just tracing it out just in space without using coordinate axes, you would just be saying, all right, I'm increasing, coming to a relative maximum, then I'm decreasing, coming to a relative minimum, then I'm increasing, coming to a relative maximum, and then I'm decreasing forever because it goes to infinity. So I would be looking at some kind of graph that would look something along these lines. Now, it may not be that perfect. It may be something that looks like this. It may look like this. But it's going to have the two hump look. It's going to be the bimodal look where you have two little peaks. All right. But it's going to increase to a max, decrease to a min, and then increase to a max again before going off to negative infinity. Right. So it could be any one of these possibilities, but at least we have a sense of the structure of the function. And then in turn, we can approximate the actual function. Like I said, going into this problem, looking at a graph, it looked cubic to begin with. So you think about the process for finding a derivative, we reduce the exponent by 1 when we use the power rule. So if we were going the other way to find the original function, we would increase the power by 1. And so we'd be looking at something that would be quartic in nature. And this is generally what a quartic function looks like. Right? So it's kind of cool in that regard, where you get an idea of what a graph would look like without actually having to know what the function is. And you'll see that as we go forward, there's a lot of techniques that we'll learn that are really just designed to give us a sense of the nature of a graph without actually knowing particularly what the equation is or what the function is. Right? So yeah, that was kind of a particularly nasty one, because if you treated that one as if it were f of x, then you drew completely different conclusions. Right? So it was kind of a trick in that regard, but that's why we're here. The concavity inflection in the second derivative test. So I'm going to just draw a quick sketch here, just to show you the concept. I'll take it as a typo. I always want to have inflection in the middle and concave down on the right. All right, so I'm gonna rewrite it, but I'll still take it as a typo. Inflection. It's really dramatic. It's so ridiculously big. I'll show you why in a second. You wouldn't think it would matter, but it matters to me. Concave down. All right. So I'm going to draw a big graph here. I'm going to make my pen go, I'll go 1 millimeter for those keeping score at home. So nice big graph here. And we're going to assume it's a function that extends on in some capacity. Not really concerned with that too much. All right. Chat coming in. Well, that's what I'm going to get to in a sec. All right. So the good question, but you'll see in a minute. All right. So we have this piece here where it's an upward facing curve. All right. Hence the concave up. All right. So concavity talks about a bow in the graph. Right. So it's a bend in the graph. It's just a question of which way that bend bends, which way the curve opens towards or away from. All right. So if it's curling in an upward direction, that we call that concave up. Right. So it curls in an upward direction. Right. So that's the definition, or at least a definition of concave up. And actually, it's an interesting Calc 3 topic where you learn about things called you learn about curvature of functions and actual curl, right? And there's curl is just kind of a more extensive topic, but the curvature of a function actually has a measure, like how curvy a function is. There's actually a vector technique that allows you to make that determination. Because some functions are more curvy than others, and it's often important to determine that relationship, right? But any kind of graph that curls in an upward direction is considered to be concave up. Any graph that curls in, you guessed it, a downward direction, concave down, is going to be considered concave down, right? So curls in a downward direction. Let's get that change made. All right. Sorry. Oh, it actually is a W. Just from where I'm sitting, it looked like a U. Color, red, curls in a downward direction. And then I'm going to shade in that part of it. Now, inflection is the transition between concavities. All right. So this would be an inflection point. All right. Inflection point is a change in concavity. All right. I'm going to have to sit up here because I can't write from the position I was in. It's like my back is kind of killing me. So I need to sit in one way or one fashion, but then it's like I really can't do my job if I sit like that. So I just got to kind of tough it out. Going for the sympathy vote here. Nah. So change in concavity is the inflection point. So that's why I wanted to put inflection in the middle, because the way I always draw the diagram is that there's some sort of concavity change transition in the middle of the curve that I always draw. Whether it's going from concave up to down or down to up, the inflection is always in the middle. So I like to have it that way. So that was the rationale behind that. So the inflection point is the change from concave up to concave down, or it could be from concave down to concave up. So another little sidebar here. I gotta go back to black. So terrible graph, but you get the idea. You have concave down, and then some sort of transition that happens that makes it go from concave down to concave up. That point in the middle, that point where that transition occurs, is the inflection point. All right. So that's all great in theory, all well and good. And, depending on the nature of the function, sometimes you could determine concavity just by visual inspection. Because if you have a good sense of the graph, and I'll give you a very, very simple case, nothing as fancy as this one with the sliders, but let's just say you have something like y equals x, I guess I need the x cubed. You look at this graph here, you have an interval on this piece here where it seems to be bowing or curling in a downward direction, and then it transitions at the origin to curling or curving in the upward direction. All right, the shape of the bow has it facing upward. I remember the mnemonic that, and it was kind of like the teacher presented it as being lame, and I always presented it as being lame, but it actually helped me. So the mnemonic that they always gave for this, or they gave back in the day, was that if you abbreviate concave up, it spells cup. And what would a cup do? Like a cup would hold some sort of liquid, and so, which shape, if you were to categorize one of these as being the shape of a cup, would it be this one or would it be this one? What does a cup do? It holds some kind of liquid. So this one would hold some liquid, but this one would spill all that liquid, right? So that was the mnemonic that they used, and it was like, all right, I can go with that. And I've given that mnemonic to students over the years, and some people don't need it, but the other people are like, oh, it's not bad. Right? So take it or leave it if you like it or don't like it. Right? But we do need an analytic approach that'll help us determine inflection points, concavity, and all that good stuff without just looking at it. Because y equals x cubed, it's pretty clear that the inflection point is at the origin. Assuming you have a solid understanding of concavity, you see the change there. If you're going to take a guess, you're probably going to guess the origin, right? But it's not always going to be that clear. Right? So I created this guided example. It's not really that guided. I just did the part where you find the derivative. But what we need to do is find the second derivative. So the process involves finding the first derivative, setting equal to 0 and solving. It's actually set equal to 1 over 0 also. That's another typo that I've been meaning to fix. All right. The first two steps are to find the critical values. All right. They set it equal to 0, set it equal to 1 over 0. All right. Then you find the second derivative. That one you only set equal to 0. All right. The result is a possible point of inflection. It's not a guaranteed point of inflection, it's a possible point of inflection. So step 5 here in this process is probably the most useless step, because it's create a sign chart. And it's like, oh, okay, great. Congratulations, you created a sign chart. What about the sign chart is going to tell us anything? Well, that's the important thing. All right. So a change in concavity means there is a point of inflection. Assuming that it's a continuous differentiable function at that point. All right. So we're always making that assumption. Like, you got to assume that the graph exists at that location. If it doesn't, then, if it's at an asymptote, it's not a point of inflection if there's no point on the graph. So there are some caveats to this, but that's the general rule of thumb. All right. So we have this function, f of x equals 1/3 x cubed. I'll pop it in 1/3 x cubed plus 1/2 x squared. So this is what my function looks like. I can bring it in a little bit. You see that there's some concavity over here. We got downward concavity, then some sort of transition in this neighborhood, and then upward concavity. All right. Now we find the derivative, we set it equal to 0. That gives me the critical values. We take our second derivative, set that equal to 0. That gives me the possible point of inflection, or point of inflection, or points of inflection, because there could be more. All right. So I'm suspecting that x equals -1/2 is a point of inflection. Now, visually, it's pretty clear that that's the case. You know, you can just kind of ballpark it. Here's -0.5. If I can get it to stay on there. That looks like the transition between concave down and concave up. All right, so going in, we have a pretty good idea what's happening. But we need to verify analytically. All right, so what we need to do is make a sign chart out of all of these values, the critical values and the possible point of inflection and any asymptotes that might be in existence. All right, so what I'm gonna do, or not in existence, depending on how you think of it. All right, so this graph, it's not a restricted domain, so it starts off -infinity. The smallest value out of the set of 3 numbers that I have here is -1. I want to stop and draw a conclusion at -1. Then I would go from -1 to -1/2. That would be the next stop along the trip, the journey, if you will. All right. -1/2 would be the next stop. We want to draw a conclusion about that point, or that x value. Then we go from -1/2 to 0. We'd stop at 0, draw a conclusion there, and then go on from 0 to infinity. All right. We want to use technology to support our work here, because rote calculation, we don't want to get bogged down with it. You know, I don't want to be overly dramatic and say, it's tedious and boring and all that stuff, but you know, to some extent it can be. But like, you don't want to spend too much time. I mean, there's a lot of values that we have to test. All right. This line here, speaking of testing values, I just put this in here just so for note-taking purposes, you would know what values I was looking at when I created the sign chart. But so basically, you just need some number that's in the interval of -infinity to -1. All right. And that number could be whatever you want it to be, as long as it's in that interval. We know that -1 is going to give us a 0, because that was a result of the computation giving the critical value for the first derivative, that is. And that would be also true for 0. So we don't really have to test anything for that. I mean, we can if we want, but we don't really have to. And besides, we know what the x value is there. These are actual x values. The value that I would choose to test could only be a -1 here, a -1/2 here, and a 0 here. All right. So, I mean, you could write it in there, but it's really not necessary. So you just kind of leave those blank. And in fact, on a test, you wouldn't have to put these values in. It's just, again, for note-taking purposes. So let's say, for example, I wanted to test the number like -5. I do anything I want as long as it's in the interval of -infinity to -1. All right. So I'm going to make this f of x so that I can use Desmos to tell me what the derivative would be at -5, which would be 20. That's a positive number. I don't care about the actual number. I care about the sign of the number. So that's a positive number. All right. If I had done instead of -5, I did -2. Same deal, positive number. -100. Same deal, positive number. It doesn't matter what you put in as long as it's in that interval of -∞ to -1. All right. The next one's a little trickier because you're living in fraction land. Negative value between -1 and -1/2, maybe like -3/4. So for example, -3/4, so just pop that in, -3/4. You get a negative value. All right, so a negative number. But just to be safe, you might try some additional values between -1 and -1/2, maybe like -0.9. Still negative. -0.8, still negative. 0.7, -6, still negative. -0.5. Now you're at that critical value. I'm sorry, not critical value. The possible point of inflection. So we're not concerned with that. But if you go beyond -0.5, then you're in a different interval. So we wouldn't consider it anymore. All right. So -1/2 to 0. Maybe I, for example, use something like -1/4, -0.25 gives a negative result. About -0.4. Oops, don't need 2 decimal points. Still a negative number. 0.3, 0.1, anything between -0.5 and 0 would be fair game. So like 0.0001, still negative. No matter what I put in that interval, I'm getting a negative number. All right. And then finally, anything bigger than 0. So like a 1, that's a positive number. 2, still positive. A 5, still positive. All right. So for example, let's say I put a 5 in there. It's a positive number. It doesn't matter what you put in. Like I said, as long as it's bigger than 0. Right. Now we talked about this last time. Sliders are a really efficient tool when it comes to this, because if I select the slider at A, now I can just kind of, suggest it, slide. All right. So I'd slide from -∞, quote unquote, -∞ to -1. All these values are 1, in which case they become negative. Right? They become negative again. And until you get to 0, in which case after 0, they go to positive again. All right. So we got a stretch of positive, a stretch of negative, and then stretch of positive again. All right. So that addresses the first derivative. What we need now is the second derivative. All right. So the method for finding the second derivative, we have the derivative function here. So the derivative function is x² plus x. So what I would just do is make that my original function. I'll just kind of go right back to snuff here. x² plus x. All right, so that's my derivative function. I'm calling it f of x, but that makes f prime of a computation involving my second derivative, right? So this here is now my second derivative. I can graph it if I want. And in fact, if I do graph it, you see that is the line y equals 2x plus 1, which is what we determined over here to be the second derivative. Right? But I want it at the point A, because I want it to spit out values for me. Right? So going from -∞ to -1, I see all negative numbers. All right, all negative numbers here up until the -1. I'll keep it south of -1. So it's still going to be, they're all negative numbers. All right. You can test whatever value you want. Like I still have a -2 written there, so I can put it at -2. It's still a negative number. Going from -1 to -1/2. So anything in this interval, right? Anything living in this interval here. Oops. So here, 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 and stopping at the -0.5. So negative 0.9, negative 0.8, negative 0.7, negative 0.6, they're all negative, all right? So my second derivative is negative at those locations, right? Beyond negative 0.5, I'm back to being positive, or I'm actually positive for the first time here. So between negative 0.5 and 0, all positive numbers. But then after 0, it's still positive, right? It stays positive after 0 also. So my second derivative is positive over this interval, all right? So we have all our signs. Now we can start drawing some conclusions, because if the first derivative is positive, that means the function is increasing. All right. So that means it's increasing. All right. If the second derivative, the sign of the second derivative matters. All right. If the second derivative is negative, that means it's concave down. So in that second interval, we have two negative numbers. So that means that for the first derivative, the negative number means that it's decreasing. For the second derivative, the negative number means that it's concave down still. All right. And so what that tells me, we're able to draw a conclusion here. This is a polynomial function. Polynomial functions are always continuous. So I'm not worried about asymptotes or anything like that. We just learned, because we have a change in whether the function is increasing or decreasing. All right. We have a change in slope, not concavity, but a change in slope. That change goes from increasing to decreasing. All right. So it goes from increasing to decreasing. So that means that whatever that point is, that transitions from increasing to decreasing, must be a relative max. And that's consistent with the conclusion of it being concave down, because the only way that you could have a function that has a relative maximum would be if there is a downward concavity, right? Because I mean, if something's concave up, how could you have a relative max over that interval? It would have to be a relative minimum, right? So then the next interval, the next known interval, we have decreasing, and we have the first derivative is decreasing, or first derivative is negative, which means the function is decreasing. So the second derivative is positive, which means the function is concave up. So decreasing, concave up. Right. So decreasing followed by concave up, that's all well and good. It's the change in concavity that matters here. Right. It goes from being concave down to concave up. Right. Changing concavity means that we're dealing with a point of inflection. All right. So there's a transition that's happening in this graph. That transition is going to happen. Well, we don't know where. I'll just ballpark it here, but it goes from being concave down to being concave up somehow, until we see that it's increasing, followed by concave up, until it hits a minimum. This should be green, because we have a change again. This change goes from decreasing to increasing. So this graph is going down, so it's decreasing, then it hits some point, and then it starts increasing again. All right. So it's increasing, then over some other interval along the way, it starts decreasing, then eventually starts increasing again, all of those transition points are important. Every one of those transition points represents something. One of them is a point of inflection. The others are extrema. All right. So in this case, at 0, since we're going from decreasing to increasing, it must be a relative max. I'm sorry, a relative min. All right. So the question is related to the third derivative and so on. In terms of the shape of a function, the third derivative doesn't tell us anything, but it does tell us the rate of the change of the rate of the change, the rate of change of the rate of change of the rate of change. So you start getting into more contextual situations. So if you think about position, velocity, and acceleration as being original function, first derivative, second derivative, then the third derivative is something called jerk, right? So that's the rate of change of acceleration. And so if you think about, I mean, my default way of representing this stuff in terms of physical ways of being, I guess, or a phenomenon, is if you're driving a car, you look at the speedometer, that tells you your instantaneous rate of change, which tells you your velocity. That's your first derivative, right? Now, how hard you press down on the gas, right? So really the movement of the gas pedal more than anything else, that's going to impact acceleration. So you're going to change your speed. How fast your speed changes is going to be your acceleration, right? So, I mean, we've all at some point been in a vehicle, and that vehicle has been at rest, and then it started moving. It's accelerating, right? So the speed is changing, right? So how fast that speed is changing is the acceleration, right? So if it's starting at 0 and increasing in speed, it's accelerating, but it's the variable acceleration, right? And depending on in what way you press your foot down on the gas, you're talking about like maybe increasing your speed substantially over a short period of time or gradually, right? So the rate of change at which you accelerate, that would be the third derivative. That would be the jerk. So, and really, I mean, if you start thinking about like, my father used to call it goosing the pedal, like when you're pushing down on the accelerator, when you're pushing down on the gas in the car, and you do it in a very gradual sort of way, you're increasing your speed, you're accelerating, right? But then there's often the instance where you're like, all right, pedal to the floor. All right, now you're talking about the jerk. Now, if you're going back and forth where you're just kind of goosing the pedal, where you're just kind of, now the rate of change at which you're accelerating is changing. So that would be the jerk, all right? So that would be the instance related to the third derivative. Now, how that manifests itself in a two-dimensional graph is kind of tricky because, you could look at a graph here, like for example, let's pretend that this is f of x. You see a rate of change here. At this point, it would be the slope of this line. I'm sorry, the slope of the line tangent to the curve at this location, right? So I can just show you that real quick. To get you a quick tangent line, all you'd have to do is, in general terms, y equals, it would be f prime of a some point a times x minus a plus f of a. I'm actually going to teach a little bit more about this. This is called linearization. I'm going to teach more about this next week, but for now, it's just a way of putting a tangent line. All right, and so depending on where I put the a value, that would give me the slope. Now, if I talk about the rate of change of the rate of change, so let's say I have a much more elaborate function, something that's like raised to the 5th power. You know, it's still a tangent line. It's an elaborate function, but then what I could do is I could start reporting all the different slopes that exist along this curve, right? So I start working my way around here, around this function, and every one of these points, at every one of these points that I move to, we have a different slope. So I can make a function out of all of those slopes. That would be the derivative function. All right. And then do the same process again with my derivative function to create the second derivative function, and then in turn the third derivative function. It can go on and on and on until you end up with a constant function. Right. So this really, the concept of multiple derivatives works out really nicely when you're getting to functions that don't converge on a particular constant value after a certain period of time, like periodic functions, for example. They oscillate back and forth between sines and cosines and things of that nature. Right. So yeah, it's intricate. You know, there's a lot of places to go with this, and so we're in the very beginning of it. And so what happens is you start looking at the ways to generalize all this stuff, and it gets more and more intricate. The more you try to, it's kind of like one of those oscillating functions. The more you try to hone in on a concept, the more expansive you find out things are. You know, like you focus in on one area of calculus and you find that it balloons into a whole other subject area, and it all gets crazy pretty quickly. You go down the rabbit hole, as you say. All right. So intervals in which the graph is concave up, concave down. This one is a rational function. You know, so I didn't want to just do the polynomial function and to leave you to suffer with the rational function on your own. These functions are kind of dicey, you know, because when you're trying to tackle a polynomial function, it's not too bad because, you know, it's power rule and that's about it. But when you get to other types of functions, other methods for finding derivatives come into play, and things can get a little kooky. But this has very normal distribution kind of look to it, and you know, there is a school of thought involved in that. If you're statistics minded and you've seen normal distributions, there is that marriage between statistics and calculus that is really kind of beautiful. And so that's another world you get into. You're like, oh, this reminds me of something from statistics, and before you know it, a week has gone by and you're still looking at that, you know. And you're like, oh, I probably should study for a test coming up. Anyway, so what we're going to do is take this one from the beginning. We got to find the first derivative, then we got to find the second derivative. And if I'm not mistaken, there is not nearly enough room to do this problem in the amount of space that I gave here. I could have sworn I fixed this, but I know I didn't. I don't know what happened. So apologies in advance, but there's going to be a lot of shrinking, a lot of resizing for this one. But when it comes to a rational function, my thought process generally takes me to in two directions. One direction is asymptotes, and then the other direction involves how to take the derivative. You can kind of look at it and say, all right, I could do some chain rule, or I could do whatever. I tend to think quotient rule is probably the way to go for something like this. Right? But before we get into that, I start looking at the domain. The graph is helpful if you don't want to get into the algebra behind it. I'm not seeing any gaps in this function. All right, so we're in pretty good shape. If you really want to be sure, set the denominator equal to 0 to make sure it's never going to be undefined. Right, so if I do x squared plus 3 equals 0, we get x squared equals -3. All right, Jolly Rancher. Square root, and so we get no solution here. I don't know what I was writing there. I just put the strike through in the wrong thing. And that's my excuse, and I'm standing by. But so we have no vertical asymptotes, even though it's a rational function, no vertical asymptotes, no discontinuities. So the domain is negative infinity to infinity. All right. Something to be very careful about. You'll notice that I don't always take the time to find the domain. In the very last problem that we did, I didn't even talk about the domain, at least in the beginning. It wasn't until we started making the sign chart that we started talking about the domain. You should always consider the domain of the function, whether it's graphically just by taking a quick look or doing it analytically. The issue is, and this is going to sound bad. It's going to sound conceited is really what it's going to sound like. Is that I'm so familiar with all these different types of functions that I have an intuitive understanding of the domain, all right? Which may or may not be true for you. All right. So if you also have an intuitive understanding of the domains of different functions, then great. You'll have to check the domain very rarely. But if you don't, then you want to check it more frequently. All right. You want to check to see if there's any instance in which the function might be undefined or imaginary. Take a look at the picture. If I see a log function, I automatically think, okay, there's a restricted domain. But when I see a polynomial functions are everywhere continuous and they exist everywhere. The domain exists from negative infinity to infinity, and there's no discontinuities along the way. How do I know that? Because that's how it's always been and that's how it always will be. Every problem that involves a polynomial has a domain that exists from negative infinity to infinity with no exceptions. All right. It's when you get into the other types of functions that you really got to make sure you check. All right. Most of the time, if somebody screws up a problem like this, it's mostly because they forgot to check the domain. So you got to be really careful. All right. In this case, if you forgot to check the domain, you'd be all right. You would have got lucky. All right. But in this one, you may not be so lucky. Although in that one, you'd be lucky too, because it's already restricted for you. All right. Because the tangent function is only undefined at, or the parent function for tangent is only undefined at pi over 2 and multiple to pi over 2 along the y-axis. But this one here, you have a vertical asymptote at x equals 1. So you'd have to be careful about it. All right. Here, you'd have to be looking for any instance in which it would be negative under a radical, although it is the sum of squares, so that would never happen based on that function. But it's a good idea to have a quick look. All right. So I'm going to go for the derivative here. F prime of x, low d high minus high d low. So the low d high, I mean, I'll write it, but the d high part of it is going to go to 0, which is wonderful. Minus high, d low is 2x over the denominator squared. And away we go. All right. So you simplify a little bit and you get negative 12x over that denominator squared. All right, we need to find critical values. Those critical values come from setting our derivative equal to 0, and by setting it equal to 1 over 0. All right, so set equal to 0, set equal to 1 over 0. And you know, it's kind of forgiving in the sense that if you forget to set it equal to 1 over 0, in many, many cases, you'll get lucky because it'll be irrelevant anyway. Right? Like in this case, I'm going to set this equal to 1 over 0. When you cross multiply, you get x squared plus 3 squared is equal to 0. Take the root of both sides. And you get right back to this computation here, which didn't have a solution anyway. So we don't have to worry about this. It's irrelevant, which means if you forgot to do it to begin with, you would have been all right because it's not relevant. How do I know? Oh, you didn't write down set equal to 1 over 0. Well, I didn't write it because it wasn't relevant. Oh, okay. All right. In your mind, you're like, well, I didn't write it because I forgot to write it, but I got lucky. You know, sometimes that plays out. Right? So, but for this one, you cross multiply, negative 12x equals 0, and you get x equals 0 as a result. I'm going to resize in a second. And so we only have the one critical value. The one critical value of x equals 0. All right. Now we already looked at the picture, so we know that that's going to be a relative maximum. All right. Now they're asking us for concavity. They're not asking us for relative extrema, but we're going to need to make the sign chart anyway, so why not, have this information. All right. I also need my second derivative. So I'm going to work off of this piece right here, this bad boy, this mamma jamma. So f double prime of x, a little bit more low d high minus high d low over denominator squared, and away we go. So it's just the high d low part of it's going to be a little bit more complicated. So the low x squared plus 3 as a quantity squared. D high is negative 12 minus the high, negative 12x. D low, that's a little chain rule there. Okay. So we have something to the second power. So that's going to become 2 times that something to the first power times the derivative of the inside, the derivative of the something, which is just going to be 2x. Okay. So we kind of earn our keep on the high d low part of it. And then it's over the denominator squared. And away we go. So that x squared plus 3 is now going to be to the 4th power. That's kind of funky. All right. Now you look at this and you say, well, how am I supposed to set this equal to 0 and solve? It's going to be a nightmare. Well, you're right. It would be a nightmare if you did it in a not so convenient way. There are ways to tackle these kind of problems that allow you to clean things up in a more meaningful way, in a more convenient way, so that you're not pulling your hair out and struggling through it. All right. So instead of thinking distribute out, think factor out. Because I notice across the board on the top, I have an x squared plus 3. I have an x squared plus 3 in each one of these terms. And that corresponds with an x squared plus 3 on the bottom. So if I factor out an x squared plus 3, I'm going to use a square bracket to keep things somewhat organized. I'm going to have an x squared plus 3, for quality 3, a negative 12 minus the negative 12x times 2 times 2x. And we'll clean all that up in a second, but all that's going to be over x squared plus 3 to the 4th power. The benefit of doing that is that now I can cancel this x squared plus 3 with one of these x squared plus 3's on the bottom. All right. Now a little distributive property. I'm going to take this negative 12 here. We take that negative 12 and run it through that other binomial. It's going to give me a negative 12x squared minus 36. These two negatives here are going to make a positive through multiplication. So 12 times 2 is 24, times another 2 is 48. So plus 48x squared all over x squared plus 3 cubed. Clean it up a smidgy more here. We have some like terms. These two bad boys, right? Yeah. So we're talking 36x squared minus 36 over that denominator. Now, when it comes to finding possible points of inflection, and by the way, it's very easy to lose sight of what the hell you're doing this for, because you do all this work and you're like, wait, why was I doing this again? We're looking for possible points of inflection. We get that by taking our second derivative, because that's what this is. This is our second derivative in a simplified form. And this is kind of the reckoning for the first unit. If you remember back then, I said, oh, you don't have to worry about simplifying. It's not a big deal. We'll have to simplify down the line. Don't force yourself to simplify when you don't need to. Now you see, okay, well, we got to simplify here because we got to solve. All right. I need to set this equal to 0. But I only have to set it equal to 0. I don't have to set it equal to 1 over 0. That makes a big difference. Aside from cutting down on the work, I don't have to worry about where this function is undefined. Now, in this case, it wouldn't have given a solution anyway, but it could have. All right. When I cross multiply here, so again, understood over 1, I'm looking at 3x squared, geez Louise, it's getting late. 36x squared minus 36 equals 0. Use your favorite method for solving a quadratic in binomial form. I personally like the isolation method. 36x squared is equal to 36. Divide out the 36, you get x squared is equal to 1. Root both sides. And you get x is equal to plus or minus 1. Right? Resizing coming up. So we just want to reconcile this with the graph and make sure that that actually makes sense. Because again, these are possible points of inflection. Just because they come through this process does not mean they're guaranteed to be points of inflection. All right. It just means that if there are going to be points of inflection, they have to come from this set of numbers. But it doesn't mean that all of these numbers are going to be points of inflection. So I could just do a quick, I like to plot the point. So I would plot -1, comma, f of -1. And just get a visual. Whether you drag the point along the curve or actually plot it is up to you. Or just eyeball it. That's fine too. But you should be able to look at it and say, you know what? That looks like a point of inflection. Or, I don't think that looks like a point of inflection. You know, one way or the other. But based off this graph, I mean, we already knew where the maximum point was. They weren't asking for that, but we already knew it. It does look like to the left of that red point is where it's kind of like having that cup look, the curling in the upward direction. And to the right of the blue one, it has a very slight, but it does have that little cup look, right? In between the red point and the blue point, it has that downward look, you know, the opposite of a cup. You know, like if you were to turn a cup over, I guess, you know, flip a cup. Idea for a game. So what we can do or what we have to do, is make a sign chart out of this in the teensy tiny little bit of space that I have left, because I'm not too bright when it comes to spacing. But again, my failing is your typo bonus opportunity. All right, so I want to make a sign chart that incorporates the domain, critical values, and possible points of inflection. So I'm going from negative infinity to -1, -1 to 0, 0 to 1, and then 1 to infinity. With the world's tiniest sign chart. Now, if you haven't already figured it out, there's a nice, easy way of filling out the sign chart. And this is kind of why that tricky question that we did earlier, this is kind of why I like to use that question to kind of get the conversation started when it comes to sign charts, or keep it moving anyway, is that if you have the graph or the derivative graph, you can build a sign chart without having to look at any numbers. It's kind of like you're working off of the conclusion to build the rest of the chart. Right. So we have a need for f prime values, f double primes, and the conclusion. And again, that conclusion applies to the f of x function, whatever the original function was. All right. So we think about where the graph is increasing. It looks like it's going uphill from left to right on the interval of negative infinity to 0. Then it starts going downhill forever. I mean, I could zoom out to make sure that that's the case, but it does seem safe to assume that it's increasing on this interval and then decreasing on this interval starting at 0. All right. So whether you want to actually test values or if you want to just look at the graph is up to you. So I can get rid of some of this stuff here and look at it by points and say, all right, from negative infinity to -1, they're all positive values. From -1 to 0, they're still all positive values because it's increasing over that interval or over those intervals. All right. Then after 0, it's all negative, whether it's between 0 and 1 or beyond 1, the first derivative is negative. Okay, so it's decreasing in both instances. That change from increasing to decreasing shows a relative maximum, which is what we were able to determine just by looking at the picture. All right, we had a maximum right there. It's pretty clear. All right. For my second derivative, we can look at the picture, or I can pop in my second derivative function, which is somewhere here. This is this bad boy. I could put that in as my original function. I only say to do it this way because Desmos kind of has a hard time with second derivatives. So we just put the original function in. I'm sorry, we put our first derivative function in. Oh, that's the problem. First derivative function, not second derivative. Dingus. So I put my first derivative function in. Function is the word of the day. Again, function. The word of the day is function. Right? So this is my first derivative. Now I would be evaluating this over these intervals from negative infinity to negative 1, all positive values. So that's concave up. Then from negative 1 to 0, so negative 1 to 0, I see some negative values there. I see all negative values. So that's concave down. All right, there's a little transition there. The transition from concave up to concave down means that we're dealing with a point of inflection. All right. Then from 0 to 1, still negative. So 0 to 1, my derivatives are still negative. Concave down. So no change in concavity, but concave down is consistent with relative max. All right. So we're kind of onto something here, because if you look at 0, this value 0, the one that we had as a critical value, has a second derivative that's negative. All right. That second derivative that's negative implies that it's concave down, or suggests that it's concave down. All right. So if you have a critical value in an interval in which it's concave down, then the critical value is a relative max. All right. Along the same lines, if you have a critical value in an interval that's concave up, oh, that was weird. I don't even know what just happened. That was so strange. It did like a duplication, and then I just kind of lost it. This is what I want. All right, so critical value in an interval where it's concave up would be a relative minimum. All right, and you'll see below that that's actually a rule. That's called the second derivative test for extrema. All right, so the last little interval here is anything beyond 1. And you can see all my second derivatives are positive. That's concave up. And you can see here that we're going from concave down to concave up. That's a change in concavity. That's another point of inflection. All right. So this was just saying, find the intervals where the function is concave upward and concave downward. We did way more than that. In fact, we just kind of discovered another rule of mathematics. So like we answered way more than was being asked. But you can see that the sign chart is really the all-encompassing answer. You know, because you really don't have to write anything beyond the sign chart, you know, to address whatever the question is asking. You know, find where there are relative extrema. Okay, I make a sign chart. It says it right there, relative max. Find where the function is increasing or decreasing. It's right there, sign chart. You see it right there, INC, DEC, increasing, decreasing. Find any points of inflection, right there. All right, so the sign chart is a really good way of organizing your work. All right, and it's also a requirement, but you know, like it's a concise way. I mean, it's a pain. It's a pain to make, especially after doing all this work leading up to it. I mean, look at all that. And I told you going in, I didn't give nearly enough room to do this work, but hopefully you understand that that's just like, I do so many things good. That's just one of the things that I don't do very well. All right, so you'll help me out with that. You'll give me the typo, I give you the bonus, and everybody's happy. All right. But this rule down here, this set of rules here, is what I was just talking about. Like all of this stuff here is this stuff. All right, everything I just wrote here is really just the ordinary speak. Well, that was an autocorrect. Ordinary speak for this mathematical theorem. Let me just take it off the line draw tool and maybe things will work out. Supposed to be an arrowhead, but yeah, that's the idea, right? So that was a lot. I'm just going to throw some stars on all the remaining problems on this page. Yeah, it's a lot. You don't have to do it all, but these are the ones that I intend to go over next class before getting into some word problems. Now you see here, you have curve sketching. We're not really going to bother with the curve sketching. It's kind of, I don't want to say it's an archaic topic, but I mean, it's kind of hard to justify the need to sketch a curve when it's like right here. So really, it's just a matter of forget about the graph. It's really a matter of being able to identify all these important things, which is what you would be doing for these questions anyway, right? So this page is kind of a wash. Then after that, we're going to get into some word problems, but I kind of went a little overboard in the word problems that I included in the packet. I figured just have way more than is needed, and things will tend to work out in the end. And now that I look at it, I realize that was probably a mistake because it's very overwhelming to look at. Next class, I'll talk to you about which ones of these examples are the relevant ones. All right, we're not going to do them all, and you're not going to be responsible for them all. All right, I'll talk you through which ones are the ones that you should really focus your attention on. Right, and then after that, we just have to talk about linearization concepts like Newton's method and differentials, and that's the unit. All right, so we're in the home stretch. This was actually the big hump, this topic. Now that we're through it, it's really just a matter of applying these skills in a little bit more meaningful way. All right, so I'm going to stop the recording at this point.